Section 3.6, position, velocity, and acceleration of a moving object. As a preparation, take a review about some related formulas and a review of fact number 1. Review number 1. These two formulas are called the definition of derivative. The formulas says that a derivative is a limit, a special limit. Review number 2. Fact number 1. Derivative at a point A is the slope of the tangent line to the graph of function f at the point P. Point P is a point on the graph of the function. The x-coordinate of the point P is A. For example, suppose this curve is the graph of function f. And suppose point P is here. At this point, there is a tangent line. Then the slope of this tangent line is derivative at the point A. Review number 3. The formula to compute the average velocity of a moving object on the time interval from t1 to t2 is this. S of t2 is the position of the moving object at the time t2. S of t1 is the position of the moving object at the time t1. This difference is the distance traveled by the object over this time interval. The denominator is t2 minus t1. This is the time elapsed over this time interval. Now, the topic today, position, velocity, and acceleration. Suppose an object is moving along a straight line, horizontally or vertically. For example, a car is moving along a straight road, or someone is dropping a ball from the top of a building. Suppose the position of the object from the origin is given by this function. Between the origin and the car, the distance is s of t. Between the top of the building and the ball, the distance is s of t. S of t is the position of the object at the time t. Now, suppose we want to find the instantaneous velocity v of a at the time a. To find the instantaneous velocity at the time a, pick a time interval that contains a. For example, pick the time interval from a to a plus h, where h is some positive number. Then, by formula, the average velocity on this time interval is the position of the object at the time a plus h minus the position of the object at the time a. This distance is the distance traveled by the object on this time interval. Then over time elapsed, from a to a plus h, time elapsed is h. Roughly, we can say that the instantaneous velocity of the object at the time a roughly is this number. This approximation is better if the time interval is shorter. That is, if h is smaller, the approximation is better. Now, let h approach 0. Then this quotient will approach some number. That number is the instantaneous velocity at A. In other words, instantaneous velocity at time A is the limit of this quotient. Recall the definition of derivative. This limit is derivative of the function s at A. So from this observation, we have a second fact number 2. If the function is the position function of a moving object, then derivative of the function at the time A is the instantaneous velocity of the object at the time A. Now, I present fact number 3. Plot the graph of the position function. Suppose this curve is the graph of the position function. Please note that this curve is not the moving path of the object. The object is moving forward and backward along a line. On the curve, pick a point, say point P, x coordinate is A, y coordinate is function value at A. At this point, draw a tangent line. Then the slope of this tangent line by fact number 1 is derivative of the position function at A. By fact number 2, derivative of position function at the point A is instantaneous velocity at A. Therefore, the slope of this tangent line is instantaneous velocity of the moving object at the time A. Fact number 3. Suppose this function is the position function of a moving object. When we plot the graph of the function, the slope of the tangent line to the graph at the point A s of A is the instantaneous velocity of the moving object at the time A. Fact number 4. Plot the graph of the position function. On the graph, take 2 points, say P and Q. Then join the 2 points with a line. By the slope formula, the slope of this secant line is y2 minus y1 over x2 minus x1. So the slope of this secant line is this number. But this number is the average velocity of the moving object on the time interval from A to B. S of B is the position of the moving object at the time B. S of A is the position of the object at the time A. So S of B minus S of A is the distance traveled by the object over this time interval. B minus A is the time elapsed on this time interval. So we have fact number 4. Suppose this function is the position function of a moving object. When we plot the graph of the function, the slope of the line that joins this point A, S of A, And this point B S of B is the average velocity of the moving object on this time interval from A to B. So in conclusion is slope of a tangent line is an instantaneous velocity. Slope of a secant line is average velocity. Here are some examples. Example 1. Let S of t represent the position of an object moving along a line at time t. In this position function, time is measured in minutes. Position is measured in feet. The graph of the position function is given by this curve. Now, part A. For what values of t is the velocity of the object 0? From this diagram, we can see that between 3 and 5, the position of the object is a constant. It is about 1,500 feet. So between 3 and 5, the object doesn't move. Therefore, the answer to part A is on the time interval from 3 to 5, the velocity of the object is 0. A second solution to part A is between 3 and 5, draw tangent lines. By fact number 3, the slope of a tangent line is an instantaneous velocity. Between 3 and 5, all the tangent lines are horizontal. Therefore, between 3 and 5, velocities are all zeros. Part B. When is the object moving in the positive direction? And when is it moving in the negative direction? The answer is between 0 and 3. The object is moving in the positive direction because between 0 and 3, all the tangent lines to the curve have positive slopes. Similarly, between 5 and 8.5, the object is moving in the negative direction because all the tangent lines between 5 and 8.5 have negative slopes. Part C. Sketch a graph of the velocity function. Velocity here means instantaneous velocity. By fact number 3, an instantaneous velocity is the slope of a tangent line. So part C is equivalent to the question. Sketch a graph of the slope of the tangent line to this curve. For the convenience of my presentation, let me copy this figure here. Now I plot the graph of the slope of the tangent line piece by piece. The first piece is from 0 to 3. Between 0 and 3, the slope of any tangent line is positive. At time is 0, the tangent line there is almost horizontal. So when time is 0, the slope is about 0. Now as time is increasing, the slope of the tangent line is increasing and reach the largest at about 2. Beyond 2, the slope of the tangent line starts decreasing. At time is free, tangent line is horizontal, so at time is free, slope there is 0. So the graph of the slope between 0 and free is at time is 0, slope is 0. Then as t is increasing, the curve is increasing and reach the top at about 2. Beyond 2, the curve starts decreasing to 0 at time is free. The second piece is between 3 and 5. Between 3 and 5, all the tangent lines are horizontal. Therefore, their slopes are zeros. So the graph of the slope of the tangent line between 3 and 5 is this nice segment on the t-axis. The third piece is from 5 to 8.5. Between 5 and 8.5, any tangent line has negative slope. At time is 5, the tangent line is horizontal. Therefore, at 5, slope of the tangent line is 0. As time is increasing, slope of tangent line is decreasing and is the smallest at about 6.5. Beyond the time 6.5, slope of tangent line is increasing. At 8.5, tangent line is horizontal. So at 8.5, slope there is 0. Now here, we plot the graph of slope. At 5, slope is 0. Then as time is increasing, the curve is decreasing and reaches its bottom at about 6.5. Beyond 6.5, the curve is increasing to 0 at 8.5. So this is the graph of slope, or the graph of derivative of the position function. Derivative is slope. Derivative of position function by fact number 2 is velocity. Therefore, this curve is the graph of velocity. Part D. When is the object speeding up? When is it slowing down? To answer this question, we need to know that speed is the absolute value of velocity. That is, take absolute value on velocity, then we get speed. So part D is asking, when is the absolute value of the velocity of the object increasing? When is the absolute value of the velocity of the object decreasing? From the graph of velocity, from 0 to 2, velocity is increasing and is positive. Therefore, from 0 to 2, speed is increasing. So on the time interval from 0 to 2, the object is speeding up and is moving in the positive direction. From 5 to 6.5, the velocity is decreasing and is negative. Take absolute value, then we can see that this curve is increasing. So from 5 to 6.5, the object is speeding up, but is moving in the negative direction. Now from 2 to 3. From 2 to 3, velocity is positive and is decreasing. So speed is decreasing. Therefore, on the time interval 2 to 3, the object is slowing down and is moving in the positive direction. From 6.5 to 8.5, the graph of velocity is increasing, but velocity is negative. Take absolute value on this curve, we will see that the curve is decreasing. Therefore, on the time interval from 6.5 to 8.5, speed is decreasing. The object is slowing down and the object is moving in the negative direction because velocity is negative. Example 2. Suppose the position of an object moving horizontally along a line after t seconds is given by this function. We only consider the time between 0 and 6, whereas the position is measured in feet with positive s corresponding to positions right of the origin. Part A. Find and graph the velocity function. By fact number 2, derivative of position is velocity. So to get velocity function, we take derivative on the position function. By subtraction and summation rules of derivative, then we have this equation. Move out the constants outside the derivatives, then we have this equation. Derivative of t to the third is 3 times t squared. Derivative of t squared is 2t, and derivative of t is 1. So this is the velocity function of this moving object. It is a polynomial of degree 2. The graph of a polynomial of degree 2 is a parabola. Because the leading coefficient is positive, this parabola is open upward. It is easy to see that when t is 2, the function is 0. When t is 5, function is also 0. So this is the graph of the velocity function. Part B. When is the object stationary, moving to the right and moving to the left? To find when is the object stationary, we set the velocity to 0 and solve this equation. Factor this polynomial, then we have this equation. Now, it can be seen that when time is 2, and 5, velocity is 0. From the graph of velocity, the object is moving to the right on the time intervals from 0 to 2 and from 5 to 6, because on these time intervals, velocity is positive. The object is moving to the left on the time interval from 2 to 5, because from 2 to 5, velocity is negative. Part C. Determine the acceleration of the object when its velocity is 0. Take derivative on velocity, then we get acceleration. The result is 12 times t minus 42. From part B, we saw that when time is 2 and 5, velocity is 0. Therefore, acceleration at 2 is plug 2 in the t here, then we get negative 18. Acceleration at 5, plug 5 in the t here, then we get positive 18. Part D. On what intervals is the speed increasing? Recall that speed is the absolute value of velocity. From the graph of velocity, between 2 and 3.5, the graph is decreasing and is negative. Take absolute value on this portion, then we get an increasing curve. So on this time interval from 2 to 3.5, the speed is increasing, but the object is moving in the negative direction, namely, is moving to the left of the origin. On the time interval from 5 to 6, the graph of the velocity is increasing and is positive. Therefore, the speed on this time interval is increasing. The object on this time interval is moving in the positive direction because our velocity is positive. Namely, it's moving to the right of the origin. Example 3. Suppose a stone is thrown vertically upward from the edge of a cliff or mass with an initial velocity of 64 feet per second from a height of 192 feet above the ground. The height of the cliff is 192 feet. The height of the stone above the ground after t seconds is given by this function. The position function is given. Part A. Determine the velocity of the stone after t seconds. To answer part A, by fact number 2, take derivative on the position function. Derivative of position function is velocity. Derivative of this polynomial is negative 12 times t plus 64. This is the velocity of the stone after t seconds. Part B. Determine the acceleration of the stone after t seconds. Take derivative on the velocity, then we have acceleration. The derivative of velocity is negative 12. So acceleration is negative 12. Part C. When does the stone reach its highest point? When the stone is at its highest point, its velocity is 0. So to answer part B, we set velocity to 0 and solve this equation. The time is 5.33. Part D. What is the height of the stone at the highest point? To answer part D, plug in 5.33 into the position function, then we get the height is this number. Part E. When does the stone strike the ground? To answer part E, set the position to 0 and solve this equation. Divide the equation by negative 2, then we have this equation. Then apply the quadratic formula to find the roots. We get two answers. One is negative, and we reject this answer. So the time when the stone hits the ground is 13.11. Part F. With what velocity does the stone strike the ground? In part E, we know that the time when the stone hits the ground is 13.11. Plug in this time in velocity, then we get the velocity when the stone strikes the ground is this number. The negative sign means the stone was traveling in the downward direction. In this example, the upward direction is positive. Downward direction is negative.